Hi everyone, this is Heather Archambault from the NOAA Climate Program Office in the MAP program, and I want to welcome you to day 2 of our 2-part webinar on Climate Program Office relevant research issues that are related to Harvey and Irma, and as well as Maria. Yesterday's webinar featured 5 talks that focused on the topics of climate attribution as well as precipitation and flooding. In case you weren't able to attend yesterday's webinar, the recording will be posted on our website shortly. So today we'll continue with the theme of looking at talks, looking at research motivated by this ongoing extremely active and devastating season, but we're going to change focus and look at predictability and prediction issues of tropical cyclones. And we're going to consider lead times all the way from extended range weather prediction into subseasonal and seasonal prediction. These webinars are part of a larger series of webinars that the MAP program has been conducting over the past 6 years. So this is the second webinar of our 2017-2018 series, and we hope you'll come back for the ones coming up in over the next several months. So please sign up for our email list if you haven't done so already. You can get to that from our MAP website. And there you can take a look back at all of the webinars we've held over the past few years. There's a complete archive on the website. So today we're going to hear from 4 speakers. The first will be Xian Zhang, and he's going to talk about the predictability of tropical cyclone genesis in a high-resolution global coupled model system. The next talk will be given by S.J. Lin, and he'll describe the performance of the FB3-based GFS for hurricane prediction, and he's also going to talk about a vision for hurricane prediction from medium-range weather prediction through sub-seasonal to seasonal scales. Then Kathy Dujon will speak, and she'll talk about real-time sub-seasonal prediction of tropical cyclone activity from this past season, taking advantage of some of the new forecasts that have just started to become available from the SubX project. And then lastly, we'll close out the webinar with a talk by Jerry Bell, and he's going to discuss NOAA's 2017 Atlantic Hurricane Seasonal Outlook. So we've allotted a large amount of time for questions and discussion today, so I hope you're not shy about sending in your message via the chat function, and you can just let me know that you have a question and I'll unmute your line at the end of the talk, or you can actually send me your question and I can read it out loud. And to mention, so this webinar is being recorded and it will be available hopefully by tomorrow. Both of these webinars, yesterday's and today's webinars, will be available. So with that, I will turn controls over now to our first speaker. Xian, are you there?
Yeah, I'm here.
Okay. So I'm passing privileges over to you. And now you should be able to share your screen, and you can go ahead whenever you're ready.
Okay, can you see my screen right now?
That looks great.
Yeah, okay. So, hi everyone. This is Xian Zhang from UCLA GFDL Joint Institute. Today, by taking advantage of this webinar on Harvey and Irma, I would be glad to present some results supported by MAP program on extended range prediction of hurricane genesis in a global high-resolution coupled climate model. Although we did not have a chance to learn similar hindcasts for these recent several hurricanes. So first of all, I want to acknowledge several of my colleagues listed here, particularly several GFDL folks, which made this project possible. So as we know, currently the hurricane prediction mainly focuses on 2 timescales. One is the short-term prediction up to 1 week. Another is on the seasonal outlook with timescale of several months. Then between these 2 timescales, namely beyond 1 week and to several weeks, the extended range of prediction or sub-seasonal prediction of the hurricane activity actually remains largely immature. So while the magnitude oscillation, the MGO, has been considered critical for hurricane prediction on this time scale, how predictable and even its predictability of harlequin activity on this time scale actually remains not very well known. So recently, the development of the global high-resolution climate model, particularly with explicit harlequin resolving capability, and improved large-scale climate variability modes that made it possible to explore the extended range predictability of harlequin activity. So, for example, at a global 50-kilometer resolution, several years ago developed the GFDL high-resolution model, high-resolution atmosphere model, HIRAM, is able to capture both the observed climatology as well as the interannual variability of the harlequin activity over the global oceans. Meanwhile, the HIRAM is also found to be able to capture the MGO modulation of the tropical cyclone TC genesis. The shown here is over the eastern Pacific Ocean. The upper panel shows this observed tropical cyclone genesis over the eastern Pacific is largely collocated with this convectively active region of the MGO, which is represented by the red. That means the enhanced rain anomalies. While during the suppressed MGO phase, the TC genesis is largely suppressed. And this observed patterns of the MGO rainfall pattern, MGO mode, as well as its strong modulation, the tropical cyclone genesis is well captured in HIRAM. With several other additional updates, the HIRAM has been evolved into the latest generation of GFDL model, the CM4, targeting for the IPCC AR6. And the representation of the large scale variability mode, like the MGO, is further improved in this new GFDL CM4. Shown in upper panel here is you can see this observed eastward propagation of global MGO is very nicely captured by this new GFDL CM4. Also, GFDL CM4 shows superior prediction scale for the MGO prediction, which shows a scale about 4 weeks. That's based on the 0.5 correlation of the MGO IMM index. And this scale is on the bar of the best of the MGO prediction model we have in the world, as surveyed by the recent Irma et al. 2004 paper. Then in the following, I will show using this GFDL CM4 to explore the extended range prediction scale for the mainly focused on the harlequin genesis. So first, I will focus on case study based on two very strong harlequin cases. One is Sandy 2012, which is well known to all of you, and another is Haiyan. It's another disastrous harlequin, the super typhoon over the Western Pacific in 2013. So all this forecast is based on actually it's based on the development version of the CM4, but close to the final version, with atmosphere resolution 50 kilometer, ocean 1 degree. We use instead of a complicated assimilation system, we just use a simple nudging approach to generate the initial condition for both atmosphere and ocean models. And a series of forecasts of 50 days is initialized daily with 24 ensemble members for each forecast. So this is the forecast results for the Sandy and Haiyan at the 5-day and 10-day lead time. So here the black star and the blue curve represents the observed TC genesis location and best track. And each dot, the red dots, as well as the gray, this curve represents the predicted TC genesis location and the track based on each ensemble member forecast. So we can see that in the 5-day forecast, while this model shows a relatively large virus in capturing the TC movement for both the hurricanes, which could be more sensitive to the synoptic environment setting model, which is more challenging. However, it is encouraging that most of the ensemble members capture the TC genesis very close to the observed location for both the hurricanes. And this in 10-day forecast, although the forecast predicted the TC genesis is a little bit more the scattering, but still quite a bit percentage of the ensemble members capture the TC genesis nearby these observation locations. Then if we define correct the genesis prediction as by the predicted TC genesis within 8 degrees from the observed TC location, and within 1/2 day before and after the observed TC genesis time. This is for the extended range forecast. So this threshold could be more generous than the deterministic predictions. So then we can define the predictive scale at each kindercast day, the lead time, as the percentage of the among the total 24 ensemble members with the correct prediction. So the here shows the predictive scale for both the Sandy and the Haiyan. We can see the predictive scale of 60% extended to the 11-day lead time. So if we take the 60% as a threshold, this 11-day predictive scale is well beyond the weather prediction scale. So this is very encouraging, particularly regarding considering we use a very simple the nudging approach to generate the initial condition of the kindercasts. Also, although we call it the high resolution global model, but the 50 kilometer is relatively very close compared to the high resolution regional weather prediction model for hurricanes. So we believe that this scale cannot be achieved for every TC genesis case. Actually, we also conducted the similar the kindercast for Katrina, and the predictive scale for the Katrina is about 6 days, about only 5 days. So the question comes that how predictable of TC genesis in general on the extended range time scale based on this model, and what's the factors affecting the TC genesis prediction scale. So for this purpose, we extended this kindercast to 11 summers, which covers more than 600 tropical storm genesis over global oceans. And due to the limitation of the computing resources, here we only conducted the kindercast every 5 days in each month with 12 ensemble members, rather than the average daily forecast with 24 members as previously for the case study. So this slide, the upper panel shows the climatological TC genesis occurrence frequency in the observations and capturing the model kindercast. So we can see that this observed TC genesis frequency largely well captured by the GFD, the model kindercast, although slightly underestimate over the Western Pacific and the Eastern Pacific compared to the observations. And then similar to the previously approach, that we can calculate the average the TC genesis scale based on the about 600 TC events during the 11 years over the Western Pacific, Eastern Pacific, and the North Atlantic. And we can see that this average the predictive scale is rather limited, only about the 30%. The maximum is about the 30% at the forecast leader 3 days. So compared to previously 60% extending to 11 days for the Sandy and Haiyan, this scale is rather limited. But it's not totally unexpected, particularly with the complexity of the TC genesis these situations. Also, due to the caveat of this prediction system previously mentioned. Then the question becomes that why some tropical storm genesis, like the Sandy and Haiyan, can be more predictable than others. So for this purpose, we just identified the tropical storm genesis with more predictable scales, which defines as the predictive scale during the first week greater than 65%. And during the second week, the predictive scale is greater than 50%. So this plot shows the location of this TC genesis with more relatively higher predictive scales. And we can see that with the green dots. Interestingly, we can see this more predictable TC genesis events is largely confined over the tropical regions of these three ocean basins. Particularly over the Western Pacific and the Eastern Pacific, the location of this more predictable TC genesis is largely collocated with the strong angel activity, which is represented by the shading, the black in the background, denoted by the interseasonally band past tilted rainfall, the standard deviation. And over the North Atlantic, the more predictable TC genesis is largely lined up over this tropical belt, extending from the west coast of Africa to the Caribbean Sea. So suggesting some role of the eastern wave for prediction scale. Relatively less predictive scale is found over the extratropical region over the North Atlantic Ocean, including the Gulf of Mexico, which is also similarly found based on the NCEP GEFS forecast recently found by the Zhou group in UIUC. So if we calculate this average predictive scale, genesis predictive scale over this more than 170 TC events, we can see the predictive scale about the 50% can extend into the first week. And also some useful prediction can be found during the second week also. So considering this is average scale over still a large amount of these TC events, I would say this is still representing some encouraging results. Then in this slide, I will show you over the Western Pacific and the Eastern Pacific, also the Eastern Pacific, the more predictable TC genesis is strongly coupled with the modulation by the larger scale forcing, including the MJO and the local synoptic scale wave chain. So the upper panel here shows the more predictable TC genesis as a function of the MJO, during the MJO different phase. We can see the more predictable TC genesis is highly coupled with the active phase of the MJO over the Western Pacific, which is also clearly seen by the sharp phase log of this tropical cyclone genesis accounts as a function of the MJO, the phase, which is mainly occurs during the MJO phase 4, 5, 6. Also, this lower panel also shows the more predictable TC genesis over the Western Pacific is highly coupled with this red means the positive 850 low-level vorticity anomalous region associated with the Western Pacific synoptic scale wave chains. So similar results can be obtained over the Eastern Pacific. I will not show here. So this result suggests that this more predictable TC genesis could be due to the strong, the large scale forcing provided by the multi-scale climate variability modes, including MJO and the synoptic waves. The MJO influence on the genesis prediction scale can be further demonstrated by this plot, which shows the average predictive scale of all TC genesis events over the Western Pacific and the Eastern Pacific. But this red is for the dueling genesis occurred during the active embryo phase, and green is during the inactive embryo phase. You can see the persistent, this much higher the predictive scale during the active embryo phase is found over the inactive embryo phase, which further confirms the important role of the MJO for the extended range prediction of the TC genesis. So, however, over the North Atlantic, due to lack of strong embryo modulation, the TC genesis over North Atlantic is less predictable, as previously mentioned. So this is the last slide I will show, which try to provide a better understanding why the dislocations prefers more the higher scale the TC genesis predictions. Here shows the extended range predictability of several large scale fields at the week 2, based on the week 2 forecast. So this predictability largely measures the consistency or similarity among the different ensemble member forecasts. So this is for the low-level verticity, and this is for the vertical shear, and this is the mid-level moisture. And interesting, we can see the previously mentioned this more location of this more predictable TC genesis over this global ocean basins. It's largely collocated with this higher predictability of large scale patterns, particularly for the low-level verticity. You can see over the Western Pacific and the Eastern Pacific, the more predictable TC genesis is largely associated with this the higher predictability, which is generally considered due to the MJO, the strong MJO modulation, and also partially through the synoptic scale waves. Particularly over the North Atlantic Ocean, you can see that this more predictable TC genesis of this tropical belt extending this West Africa coast to Caribbean Sea is well collocated with this higher predictability of large scale patterns. However, I believe that the climate or weather regimes that provide this subseasonal predictability over the tropical Atlantic is still not completely well known. And for example, the whole predictable of this easter wave activity on the extended range time scale needed further studies. Also, as I mentioned previously, due to some caveats of this kindercast system, we use the very simple initialization scheme, also the relatively coarse resolution compared to the weather prediction model. There could be some of the unexploited predictability source missing in this model, which could be more interesting to explore to do the similar analysis based on the more realistic this NGDPS predictions, which will be introduced by the following the presentation by SDLin. So since I think that my results are relatively straightforward, I will just leave the summary here. I'm glad to take any questions you have. Thank you.
Dan, thanks so much. Very interesting. While I see if any questions come in over the chat, are there any questions in the room? So as a reminder, yes, you can let me know the Q&A or the chat function, either one, just that you have a question, and I'll unmute you, or you can just type your question if you prefer me to read it. Question, Chin. So were you looking at just the peak tropical cyclone season for this, or is this year-round? And also, have you stratified or looked at your results in the context of different times of the season at all?
Yeah, this result mainly based on from June to October season, summer season.
So everything is grouped in that time. Have you thought about looking at the early part of the season versus the later part and how your results might change at all?
Yeah, I haven't analyzed the seasonal variability of this scale, not yet. Yeah. Could be interesting.
Thanks. Well, at the moment I don't see any questions, but can you stay on the line for? Oh, sorry, there is a question in the room.
Yeah, sorry. Hi, Sean. This is Anarita. I was just wondering, could you summarize the kind of sources of predictability that you see for TCs over the Atlantic region? I mean, I heard you say easterly waves, but it would be useful if you could kind of summarize those.
Yeah, so based on the results, because the more predictable TC genesis is largely aligned with the tropical belts where the easter wave are active. So this is the evidence that the easter wave could provide the predictability for the extended range of TC genesis prediction. But however, the whole predictability of the easter wave activity beyond the weather time scale, they haven't known because we haven't analyzed this based on these kincasts. So this is an interesting topic for the future study. But we have evidence that the easter wave will provide this predictability based on these results.
Okay, thanks so much. Shan, maybe you could stay on the line, and if there are any questions, anyone in the audience, if you do think of a question, feel free to just chat it to me at any point during the webinar, and if we have time at the end, which I think we will, we can go back and revisit any questions that come up. So thank you.
Yeah, thanks. Yeah.
Okay, so now we're going to move on to our next talk, and this is by S. Phelan at GFDL. And I transfer to the right person here. Okay, so S.J., are you there?
Yes. Can you hear me?
Are you there?
Can you hear me?
Yes. You sound very faint.
Oh, I have my mic here. Is it better now?
That sounds a little better. Just yeah, whatever
Okay.
you just put there. That works.
All right. If the sound quality is okay, then I would go ahead.
Okay, great. We can see your presentation. Go ahead.
All right. So everybody, this is S.J. Lin from GFDL. I will be speaking for the GFDL FV3 team on our latest effort on improving the forecast system from short range to subseasonal. And so that's what I call a long range hurricane prediction. Long range means it's way beyond 5 days. And I believe the lesson from Hurricane Rita and Harvey, the recent Hurricane Harvey, teaches that long-range precision is really very important for the society. So the theme of my talk would be, first everybody asks the same question. Why is the European model, the IFS, is the best NRAP model? And in particular for hurricane track prediction, I would say something about their intensity prediction. That's not so great, but their track is no dispute the best. So we need to dissect and learn from them. And regarding the strength and the weakness from the best NRP model in the world. And then I will talk about the research and development plan for the long-range prediction, and based on our past experience and the recent development. So we are talking about strengths and weakness of the European model versus the GFS and the FV3, which is supposed to be replaced the GFS. We look at the kinetic energy spectrum, and this plot really tells a lot of stories, and more than you may think. I always say that the kinetic energy spectrum is the fingerprint of the model's dynamics. Whatever you touch, you can tell from this plot in the diffusion. And the diffusion, and if you look at the observation aircraft analysis, it shows a very nice straight line of Mach 3 spectrum, synoptic scale. Some people call it 2D turbulence. And then there's a transition to mesoscale, Mach 5 third. So as you can see that the European model that's the red here does not at all simulate the mesoscale, but it pretty much follow the synoptic scale all the way to the 4 delta x limit. And FA3 on the other hand has a beautiful, almost perfect mesoscale spectrum here. So this is the theory. It's almost perfect, down to 4 delta x. And GFS on the other hand is not very good. It has energy that's 3 orders of magnitude lower than it should be. However, it has a very interesting behavior as well. It shows a quick drop near the start of the mesoscale, and then recover to try to make a Mach 5 first spectrum, which the IF does not do that at all. And it actually cut it out very sharply at the end. Now you have to ask the question, what's the best for numerical short-term numerical weather prediction? I think this is really the key here. That, for example, FA3 that's built from a climate model at the beginning life as a climate model. We pay attention to conservation and all the AD transport, etc., and try to best that we can, but you are not comparing with real forecast. But when in real forecasting situation, the mesoscale you can resolve, yes, but doesn't mean it's correct. Because if you don't have the right initial condition, what you are resolving, what you are trying to generate may actually hurt your forecast. And so we take a lesson here. And we can play with the dynamics, change the diffusion or change the implicit diffusion or explicit diffusion. However, I have gone through a lot of experiments that the external diffusion that you added doesn't really do it. It's really something like a very dramatic diffusion that you put into inside the dynamic, inside the equation scheme. So you have to basically do some surgery to my old scheme. And we can actually start to mimic the behavior of IS, kill a little bit of the mesoscale for the sake of better skill score. You could do that. So here's the evidence. After a year of experiment, so on the now for analysis, the first number you want to look is the 500 millibar high anomaly correlation. And I would say later that generally people, well, I don't live on 500 millibar high, who cares? But actually, that is really good index of the quality of your large scale, which in turn actually determine how accurate you can predict the hurricane track. So this is a very important index, not just for the sake of beauty contest. So as you all know that if you start, so this is FA3 with GFS physics, but we change the microphysics and change the dynamic quite a lot recently. This happened in the last 3 to 6 months. So this is the relative skill. The horizontal line is GFS. Anything higher is better. So as you can see, the IFS is significantly better than GFS. This is for a whole year period. And we do a lot of experiments, try to match IFS. So we start out with the GFS initial condition. There's nothing we can do to overcome the initial deficiency in the initial condition. However, I think we can overcome the deficiency in the initial condition with something in the dynamics as well in the physics, and that's what we got. So after several months of intense tuning, we were able to discover that we can actually beat IFS forecast, even using GFS initial condition, but it only happened at very late time. So if you don't have a very good initial condition, if you have a better model, you could probably overcome it, but at a much later time. And that tells you the deterministic forecast. Back to the first slide I showed about the when you are resolved, this version of FA3 is heavily dense. But yet the kinetic energy spectrum is still slightly better than IFS. So at the expense of some of the mesoscale structure. So instead of simulating incorrect mesoscale structure, you kill it and from the model, and then you can do this. So this is one lesson. So we this is the recent development, but we have been running real-time forecast using a slightly older version for a year now, and the we also do a high cast, go back 2 years. So this is the result because today's topic is the hurricane. So this is just showing the hurricane. We have some other results, but this just shows you the hurricane. So there are more than there are more than 1,000 cases, and this is global statistics for the past 2 years. So the statistics are extremely robust because it covers thousands of cases. And you can see that the red curve here is the FV3, we call FV-GFS, because it's using almost the same physics as the GFS. The trace is only slightly better, and the European model has no doubt the best in the track prediction. As I mentioned, perhaps they kill the mesoscale structure, and they maintain the integrity of that scale, and they get the hurricane track very good. This is supported by the plot on the right, because if you look at their intensity, the European model has no skill whatsoever in the intensity, but the media probably only focus on the track, but their intensity is horrible. But intensity skill is not so good. Even GFS is significantly better than the European model. And the surprising finding here is that the FV3 at 13 kilometers actually has almost the same skill in intensity as the best intensity model in the world. That's the H-Wolf, and which has 5 times higher horizontal resolution. So we look deeper into the intensity issue, particularly with GFS. And we know that actually GFS tend to develop much stronger hurricane than every GFS or European model. But those are only mostly in the sea level pressure measure. And so a better way to look at the intensity distribution is the 10-meter wind and sea level pressure correlation. The blue dot shows the operational GFS, and the red dot is the FV3 with GFS physics, initialized with GFS, and the black dot are the best track data. So you can see that in particular over Pacific Ocean, Central Pacific and Western Pacific, the GFS sea level pressure can go as low as 860 millibar, way below the observation. However, they don't have the wind to match. But using the same physics, just replacing the dynamics and doing exactly the same forecast, shows that with the FV3 dynamics, the wind and sea level pressure correlation are much closer to the observation for all the basins. And this is also a very robust statistic because it's based on a full-year test case, a single run every day. So now I like to focus on the recent event, Hurricane Harvey and Irma, using the same forecast, real-time forecast system. That's a little bit old, again, not our latest, but it shows you the promise of this modeling system that for the Harvey, it's a very difficult storm to predict because it kind of very slow moving, and also after landfall make eastward turn and stall and make landfall again. So it's a very tricky storm. But as you can see, this is throughout the whole life cycle of Hurricane Harvey. Okay, every 6 hour forecast, every 12 hour forecast. I'm sorry. So overall, you can see that the UK Met Office model actually surprisingly is much better than everybody else for the first 3 days, and they gradually decay, not so good at day 5. But day 5 is important for Harvey. 5-day forecast is very important for Harvey because all the heavy precipitation, you can predict heavy precipitation 5 days in advance. If your track at day 5 is still reasonable, and I will show that in the later slide. And in this case, for compared to all the operational global models, the FV3 is the best. Actually, significantly better than IIS at day 5. And initially, I guess there's a lot of factor involved, including the initial condition, and so we are pretty much the same. But this is not a shocker. For Hurricane Irma, IFS is the best capital, the best for Irma, because obviously that the impact of initial condition data accumulation shows up big time here, and they are in a class of their own, and nobody come close. And the FV3 is a close second, but no, not close second. I'm sorry, it's a distant second. But it's still not doing a bad job at all. So go back to Harvey and the long-term importance of long-term prediction, the track. In this case, for Harvey, the intensity, wind speed is important for a short while, but the position is really the predicting the correct position in long term. It's the key to predicting the correct precipitation, long range prediction. And this has a lot, I believe that will have a lot of benefit to the society. And here we show the 13 kilometer real time on the left version, and on the right is our global model, also roughly 13 kilometers, but we're implementing a nest. Despite for Atlantic basin, not really for Gulf of Mexico. As you can see, the boundary is drawing over Texas. But even with this handicap, it still do a very decent job forecasting the not only the track, because if you don't have the correct track, you are not going to predict the precipitation correct. So both model different, same model but different resolution show that, for example, the peak value is actually over 28 inches from the 13 kilometers, and from the 3 kilometers, it actually predicted a 33-inch precipitation 5 days in advance. So I'm going to Hurricane Irma. So this is kind of a look into the future, and this is the simulation model simulated radar reflectivity compared to observation. The reason I'm showing this is for hurricane prediction, I believe it's simultaneously a global problem and a regional problem. You cannot just have a regional focus, because the driving force is really global. Even a decaying typhoon in the Western Pacific would have some impact to the hurricane position in the Atlantic Ocean. So hurricane model is a global problem and a regional problem. And here we are approaching, proposing a modeling system that maintain the global circulation integrity, so that you can get a better precision. And simultaneously, we want to have a very high resolution nest. Well, ideally, you want to go to a global cloud resolving model, but we don't have the computer to do that yet. But so in the meantime, that we can do this economy way of taking the best of both approach, embedding a high resolution nest that's actually constantly communicating with global model, so that you can get the precision right. But the nest will get you the simulation, the intensity and the precipitation simulation as good as you can get. So going to that thinking that this has been going on, seasonal hurricane predictions research has been going on at GFDL for almost a decade already. And we published a paper back in 2011 in GIL, reporting the remarkable feasibility of the internal availability of a hurricane. And here we show that for the 10-year period, the seasonal prediction is almost perfect. Correlation-wise, the model to observe correlation is greater than 0.94. That's an unbelievable skill for seasonal prediction. But that's for that period. That period turned out to be spectacularly predictable. and later year is less predictable. But so we do a 25-year reforecast for the seasonal prediction, from 1990 to 2014 for 24 years. We also recently switched the dynamical core from a hydrostatic version of MV3 that we used before to the latest MV3 that's used for the NGGPS. And we show that with this switch and a lot of retuning, that we can get a slightly better correlation. And for the 25-year period, we also get some improvement. So this is very encouraging. The reason we try to push non-hydrostatic dynamics is this is really the foundation of the unified modeling system. When you want to do the unified prediction from all scale, you have to be able to do from cloud scale to very large scale. And non-hydrostatic dynamics is really the key. And I don't have the time to show, but actually in the stratosphere, something funny going on. Once we start using the non-hydrostatic dynamics, we start to simulate QVO correctly by its own without actual periodization. But that's another topic for the future. So I want to keep on the theme of the seasonal prediction that out of that 25-year seasonal prediction, we are examining the quality of the NJO simulated during the seasonal prediction. And on the right, it shows the precipitation homolog diagram. As you can see that the magnitude, this is not couple version, it's just atmosphere only. So the magnitude.
SJ, we can't hear you anymore. Are you there?
I'll be right with you.
Okay, thanks.
Can you hear me now?
Yep, you're back.
Okay. All right. I use another mic. So on the left, we show the quality of the NJO prediction, simulation of prediction, because it's a 25-year statistic. And the uncoupled high range show a very promising skill, particularly in the phase propagation. May not be the magnitude, but we believe we can further improve this after coupling. That's work in progress. And on the right, we show the impact of the NJO over the Gulf of Mexico tropical cyclone activity. And you can see that observation versus highway. And the top panel is enhanced, convective enhanced phase of the NJO. The bottom panel, the bottom two panels shows the convectively depressed state. And it clearly demonstrates the impact of the successful MJO simulation for seasonal hurricane prediction. All right, now I'm back on track. So so we started using that version of a high-range hydrostatic version that has the latest double pun convective polarization from CM4. And we started doing the kind of retrospective high cuts and using Hurricane Irma as a demonstration of the usefulness of the ensemble prediction based on this is relatively low resolution, but it's still non-hydrostatic. C384, that's about 25 kilometer resolution. So it shows a very promising capability using the Hurricane Irma example, showing the ensemble prediction actually very, very close to the actual track with the 5-day lead time. So this is my final slide, so sorry for the delay. So I would like to propose a hurricane prediction system that actually can resolve hurricane and can be used for really long range. By long range, I would be thinking at a minimum 0 to 30 days. And to do that, lots of requirement in the model, and And we already know the importance of MJO prediction. I think we are on the right track. And the most important difference we are proposing here is we believe we can take the best of both worlds. On the left panel here showing is the global brute force approach. Global showing the promise of a current resolving model for long-range prediction. And if I don't tell you which one is the model prediction, which one is the Himawaரி satellite, you probably have a hard time to locating which one is model, which one is satellite. This satellite is the highest resolution satellite, Japanese satellite. And I believe our model really almost capture the similar details as the high resolution satellite. And we want to be able to use this type of model effectively, computational effectively for long range prediction. And the way to do it, we believe we have a very, Lucas Harris at GFDL has developed a very nice two-way interactive global to regional approach for hurricane prediction that simultaneously maintain the large scale circulation, and yet we can resolve hurricane in a very economical way. Thank you. And I will answer any question, if any.
Great, thanks, SJ. So if anyone has questions, go ahead and send me a message through the chat function or the Q&A box. Are there any questions in the room?
This is Narita again. I'm going to ask the same question that I asked before. So can you comment on predictability sources for the Atlantic for hurricanes? I mean, you mentioned results for hurricane counts on seasonal timescales, and then you mentioned MJO, easterly winds. Can you just kind of wrap all this up for us?
In what I expect, I'm sorry. I believe the Atlantic hurricane prediction it's out of all the world's basins, Pacific, Indian Ocean, and Atlantic, or East Pacific, West Pacific. Atlantic basin actually has the best chance of long-range prediction. It's very much strongly controlled by SST anomaly. And certainly the land surface model also play a very important role. So once we capture all this stuff and the model allow the model to be able to simulate strong major hurricane, I think we have a very good chance of success. Because there's a strong natural predictability, built-in predictability. Does that answer your question?
Yeah, I understand that. I think SSTs are a big major control over seasonal timescales. Is that your point?
Yeah, and we want to control the external influence. The SST is in situ influence, and the external influence is the global circulation. So you want to have a global modeling system that actually can faithfully predict the large scale changes at a time of 0 to 30 days at a minimum. That's the MJO time scale. And I think those are the key. And I believe we have a modeling system that's almost ready to do it.
We do have a question. Jan, I unmuted you if you'd like to ask it. Are you there?
I'm sorry, are you asking any questions?
Oh, I'm asking Jan Zhu, who had a question, but I can actually read it, I guess. Let's see. So the question was just, I guess, picking up on that, the role of ocean initial conditions, which I think, we just sort of talked about. But if there's anything else you'd like to say, I'd say, in terms of prediction. SJ, are you there?
Yes. I'm sorry. Although the ocean initial condition, I believe that for now we have found that if you improve the ocean dynamic, that will allow better simulation of MJO, obviously, and so that will give you another push to a higher predictability. But even without ocean coupling, and we can probably get by with the mixed layer ocean in the very beginning. and that would get us started. So maybe it's I don't know, it's correct, scientifically correct to say that ocean coupling is not important for Atlantic hurricane prediction, but that may be too strong a word. But I believe that the first order effect is really in the initial SST anomaly, and the ocean coupling would be the second order effect, and then the external influence through, say, for example, MJO propagation.
Okay.
And then and they also needs ocean coupling anyway.
Okay, great. Well, in the interest of time, I think we should move on. Thanks so much. And say if you want to stick around on the line, we can come back to you if there are any further questions. Okay. Hi, Kathy. Are you there?
Yes, I'm here. Can you see my screen and hear me?
We can see your desktop, and it looks like you're in full mode. Okay, great. So Kathy Bajan is next, and she's going to talk about some, I think, some early results with SubX.
Yep, thanks. Yeah, so I'm Kathy Bajan. I'm from George Mason University in COLA, and I jointly lead the SubX subseasonal experiment, also called SubX, together with Ben Kurtman. And I just want to acknowledge that this is a large team effort. And I'll highlight in a couple of slides who all those people are that are involved in this activity. SubX is a climate testbed project supported by NOAA MAP, as well as the Weather Service, ONR, and NASA. And so what I'll show you today is I'll give you a little background on SubX and what we've been doing, and then I'll show you some real-time forecasts that were made during the Harvey and Irma period. So an overview of SubX, we have 7 global models that have produced 17 years of retrospective forecasts. These groups are also producing 1 year of real-time forecasts, and these real-time forecasts are made every week. They began in a preliminary testing context in early July, and then we had all the models in and going real-time as of August. These forecasts are used to provide guidance for CPC's week 3 and week 4 outlooks. And all of the data from our hindcast and forecast have been released. They're released in mid-August, and they are constantly updated. And by release, I mean they're publicly available. And I'll give you some information about that near the end of the presentation. So this project is focused on subseasonal prediction, so focused on that week 3, week 4 time scale. And we have a whole group of models that are all participating in this activity, and each of those groups have a sort of a team of people that are involved in dealing with the model reforecast, forecast, data handling, and evaluation of the models. And so for this project, we have a protocol that the models have to, each of the modeling groups have to follow in order to participate. And that protocol to start with is that the prediction system details are up to each of the different modeling groups. So what that means is resolution, how you initialize, how you do perturbations, whether you are contributing a coupled ocean atmosphere model or an atmosphere only. All of those are up to the different modeling groups to provide their modeling systems that they have. However, the real-time and the retrospective systems must be identical. So whatever you run reforecast, whatever system you use for reforecast, you have to use the same system for the real-time forecast. We have a reforecast period from 1999 to 2015. We require at least 3 ensemble members. We encourage more, and most of the groups are providing more, and especially in real time, they're providing more. The minimum length is 32 days for the reforecasts. And the operational requirement is that the real-time forecasts have to be made available to CPC every Wednesday by 5 p.m. of every week. So again, these are weekly forecasts that are being made. And that data is being provided to CPC to support their operational forecasts, as well as to the IRI data library for research purposes on a 1 degree by 1 degree grid. So we have a large set of variables that people have asked for and want to look at. And so we had to kind of prioritize in order to handle that large data set. So we're starting with these priority 1 variables that are required to support CPC operations. And so that's a group of 10 very common variables that people are interested in, including geopotential height, winds on 2 different levels, temperature precip, surface temperature, and OLR. So given this set of variables and the set of real-time forecasts that we have, I want to look at sort of 2 questions today. First is, how far out did the sub-X models pick up on Harvey and Irma-related precipitation? This is a really tall order for the subseasonal timescale. We don't expect these models to be predicting tropical cyclones out at weeks 3 and weeks 4, but we want to see that they catch the precipitation, a large amount of precipitation, or at least some indication of a large amount of precipitation at these longer range timescales. And then probably what's more realistic for the subseasonal timescale is to be looking at large-scale environmental factors for favorable or unfavorable conditions for tropical cyclones. So we'll take a look at how well the models did with one of those factors. So just to give you kind of a context for the forecasts that we're making, kind of how they fit on a calendar. If you think about Hurricane Harvey, we'll look at the August calendar, and Hurricane Harvey hit Texas on the 25th, and we have forecasts that are produced by 5 p.m. every Wednesday. CPC collects them all on Thursday, and also we'll take a Thursday Canadian model because of its special agreement. And then combine all those forecasts and make a week 3, week 4 set of forecasts from these models to inform their operational week 3, week 4 forecasts. So if we have forecasts that were all collected on Thursday the 3rd, then we can think about a week 3 period that goes from their forecast period begins on a Saturday, so a week 3 period that begins on the 19th and goes through the 1st of September that would encompass Harvey. And then we can also go the following week set of forecasts and say we would have a week 3, week 4 forecast that starts on the 26th and goes out 2 weeks, and that would encompass the period of excessive precipitation that occurred following Harvey. So this shows you here our multi-mean ensemble week 3, week 4 forecast of precipitation. This is total precipitation. And this is for the period, valid for the period of August 19th through September 1st and August 26th through September 8th. And so what we can say from this is that, of course, there's no clear sign of, a tropical cyclone in this, but we can say that the models seem to think that there's reason for larger amount of precipitation in the southeastern U.S. Than in the rest of the region on those timescales, whether that's associated with the model thinking there's a tropical cyclone, or whether that's associated with other factors in the model. It's hard to say. You certainly can't say from this evaluation that these are our forecasts that we've produced for these 2 periods. So we can kind of look into that a little bit more and say, well, how did the models do over sort of different lead times? So what I'm showing here is the total rainfall for the week of October 26th through September 1st. So that's the period following Harvey's landfall that would have was the period of excessive precipitation in Texas. And I'm showing you here an ensemble mean for each of the different models. So each column shows a different model. And I'm showing for different lead times, so week 1, week 2, week 3, and week 4. When we first started, we had 3 models participating, so that's why a few of the models here don't show up. But then by the next forecast, we had all the models participating. And so if you look at it, that week 4 period, what you see is, again, the models seem to think that there's some reason for more precipitation in the southeastern United States than in the surrounding areas. But again, it's not clear that why they think that or that we would expect the models, we certainly wouldn't expect the models to pick up on a tropical cyclone this early on. If we look at week 3, there's some evidence that a model perhaps thought there was some kind of specific event that might have been a tropical cyclone. But that in general, the models are showing a lot of precipitation, but they're not really, it's not clear why or where that's coming from. As you go into week 2, you start to see a little more evidence, but you also see what might be associated with any sort of event-type situation track. You see that shifts around. So the models maybe are picking up on something, but they don't have any clear idea of what's going to happen at that time scale. And then by the time you get into week 1, which is weather prediction time scale, it's not surprising the models are very much picking up on the large amount of precipitation. We do have a couple of models that didn't pick up on it, and we have a variety of different initialization techniques and methodologies going on. So that's something we need to look into in a lot more detail to kind of understand where maybe some model initialization issues are coming in. But we do see that at week 1, we certainly see evidence of heavy precipitation. So in order to try to identify if that precipitation is associated with an event that might be a tropical cyclone, variables I have to work with involve wind. So this is showing you the weekly average wind speed for that week. And this is a weekly average and an ensemble mean, so we certainly don't expect to see tropical cyclone force winds in this, but I'm looking for kind of localized evidence of winds and kind of a track-like orientation that might indicate the models are picking up on something that could be a tropical cyclone related situation. And so we do see some, sorry about that, we do see some sort of localized wind type situation even out at week 4 that might be related to tropical cyclone. But again, this is pretty far out for these models to be trying to predict tropical cyclones and their related precipitation. So really what we think we can capture at these timescales is large-scale environmental factors, like Shannon mentioned earlier, like shear, moisture, vorticity. So here I'm looking at shear. I'm just looking at weekly average zonal shear for the week following Harvey's landfall. So that would be consistent with this situation in which we had very favorable conditions for tropical cyclone activity. And the way the colors are set here is that low shear are the darkest red. So that means your strongest likely conditions for tropical cyclone activity. And so what you can see is that at weeks 3 and 4, we can see that the models captured this situation of low shear and high potential for tropical cyclones. And so then just to follow up quickly with what Irma looked like, I'm showing you here the weekly total rainfall for the week of September 9th through 15th. And again, this is the ensemble mean and the 4 different week lead times with the different models as the columns. And so you can see early on at the week 4 time scale, some models seem to think there should be enhanced precipitation, but it's really all over the place and not at all clear that we could predict such a thing at week 4 time scales. Even at week 2, again, lots of precipitation, but no clear, no clear connection with the track of Irma. And it's really only at week 1 time that you see sort of this localized precipitation that you could associate with a hurricane track. So again, this is not surprising. We don't expect the models to be able to predict tropical cyclone-related precipitation at these longer timescales, and we really think that focusing on the large-scale environment for weeks 3 and 4 is probably what's more important. So to summarize, the sub-X models were able to predict increased precipitation at week 3 and 4 associated with some sort of event, particularly as it's shown in the Harvey plots, but certainly not any details, and it's not clear that that event was a tropical cyclone. But it did seem to be associated with localized winds. Some of the sub-X models appear to predict tropical cyclone-related precipitation at 2 to 3 weeks, particularly with Harvey, but tracks and landfall locations cannot be predicted very well this far out. But the sub-X models did predict low shear environment at 3 and 4 weeks during the post-Harvey and into Irma period. And so we want to focus future work on evaluating the skill of the sub-X models in predicting these large-scale environmental conditions and see if we can produce even both evaluation and retrospective forecasts, as well as providing some real-time information in the future of areas where there may be more or less likely potential for tropical cyclone development. So the last thing that I want to tell you about is that these sub-X forecast and hindcast data are publicly available. So you can go to our website. You can click on this little button that says Get Data Here. That will take you to the IRI data library where all of the data sits. And you can also click on this menu here for data and get more information about the data, what data is available, how it's set up, as well as some codes for downloading the data. So I encourage you to go take a look and see if you can want to, especially if you're interested in more information about the forecast or the hindcast and how well the models did in terms of predicting tropical cyclones or other aspects of subseasonal variability. Thank you.
Kathy, thanks so much. I see that we already have a question. Are there any questions in the room before we go to the chat? Okay, I actually see a question from Augustin. And I will actually unmute you. If I can get to Augustin, are you there?
Yes, I'm here. Can you hear me?
Yes, we can.
Okay. So, yeah, Kathy, is the precipitation that you were showing for week 3 and 4 bias corrected?
So this is total precipitation. So no, this is not bias corrected. It's not anomalies. We're simply showing the raw total precipitation from the models at this point. Bias correction anomalies is coming, but that's we haven't gotten to that point yet.
Great. So Kathy, you mentioned kind of looking at TC activity more broadly. Are you going to continue with this work specifically focused on this season, or do you think that TAC will be more, more broad than that in terms of next steps?
You mean in terms of looking at tropical cyclones in relationship with that?
Yeah. Will you do the case study analysis, do you think, or will you will the next thing to be looking more generally at tropical cyclone activity in the sub-X models?
So from my own perspective, I think kind of a broad look at through the retrospective forecast and looking at the connection between these large-scale environmental factors and the development of tropical cyclones over many seasons or many years. But I do think there's room for a case study, and I think there's been some at our recent NME sub-X meeting. There was discussion of interest in case studies associated with this particular season, and given how active the season was, I think it would certainly be worth investigating it in more detail.
Great. I actually see one more question. Brad, I just unmuted you if you'd like to go ahead and ask your question. Actually, maybe you're not actually connected, so in that case.
Oh, I'm sorry. I was on mute. I'm sorry.
Okay, go ahead.
Great presentation, Kathy. I'm wondering, is the skill for atmospheric rivers higher at 3 to 4 weeks or even at 2 weeks when compared to, say, tropical cyclones? Because I know it's a little bit more difficult, the tropical cyclone track. But I'm wondering if you have any success with larger scale features like atmospheric rivers.
Yeah, so we certainly haven't looked at atmospheric rivers in sub-X yet, but I think both of them have, both tropical cyclones and atmospheric rivers, because of their connection to the tropics, and especially connection with MJO, there may be potential to look at that, look at atmospheric rivers as well, and predictability there. My understanding from, I've spoken with Emerson LaJoy and Dan Collins are on the sub-X project, and they're at CPC, and they say that they saw by looking at the global forecast pictures, they saw some large-scale streams of what they thought were atmospheric rivers during this same time period, and so it's certainly something we'd like to look at.
Thank you.
Okay, so I don't see any other questions. Oh wait, it looks like there may be one additional question from James Halgren. I'll just read this in the interest of time. So it says, Kathy, extending the question on atmospheric rivers, what other skill metrics for broader precipitation observations have you computed?
So we're in the process of computing skill, but we have not done our full skill evaluation yet. These are, so what you're seeing here is really our kind of hot off the press, fresh, what we've really preliminary results. And so we're in the process of looking at the skill of, and we'll do standard skill metrics, probabilistic skill, of temperature and precipitation, because that's what, because that's what supports CPC's operational effort. But we also have interest in phenomenological skills, so the MJO, skill of MJO, skill of NAO, and things of that sort.
Kathy. And one more question from in the room.
Yeah, hi Kathy, this is Anarita. Nice talk. I was wondering whether, so I think you showed some results showing some sort of, hint of these events, on a large scale field, several weeks ahead, at least I think 2-3 weeks ahead. And I'm wondering whether you have a sense of where, this predictability was coming from in this case, what was kind of preconditioning the forecast.
And so I did do a quick look to see what the status of the MJO is, because I've previously looked at some things involving MJO and tropical cyclones, and it didn't appear in this particular case of Harvey and Irma that the MJO played a big role, although I didn't investigate that in a lot of detail. But quick look didn't imply to me that that was the case. I honestly think that this, this time of year is highly climatologically favored. This really is the peak of the season, and so then trying to understand why why are the SSTs so high? I didn't talk about that here, but others have talked about the SSTs. Why is this year so low? Is that just climatology and it just happened this year, or is there something more going on? I think has to be investigated.
Thanks, Kathy. I think that's a very nice lead-in to our next talk, actually, by Jerry Bell at CPC. But thank you very much for your presentation.
Thank you.
Okay, so now we're going to move to the final talk of this webinar, and to take a look at the conditions that may have been anticipated for this very active, so far, Atlantic hurricane season. So Jerry, it looks like you've already shared your screen, so just take it away.
Okay, thank you. NOAA's been issuing seasonal hurricane outlooks since 1998, and since about 2008, when we've been able to use various dynamical models to help with the seasonal outlooks, the skill has gone up tremendously. Also with, research, doing more predictions, monitoring, and so on, we can often make an intelligent statement about what the overall strength of the hurricane will be. So NOAA's seasonal hurricane outlooks are official product of the Climate Prediction Center, but they're made in strong collaboration with forecasters from the Hurricane Center and also the Hurricane Research Division. The website there at the bottom shows is where you can get the history of the hurricane outlooks and a whole suite of conditions that are associated with the hurricane season. Many different animations of key things like the vertical wind shear, ocean temperatures, velocity potential, stream function, winds at various levels, and so on. So you can monitor a lot of the key conditions throughout the season from that website. Now, overall, this is a map showing the 2,000 storms, tracks of the storms to date that I just pulled off of Unisys Weather. And it's been a very active season, classified officially as an extremely active season. But what I'm indicating here is not just the storm tracks, it's that green box. That green box is called the main development region. It is the activity and the conditions in that green box that determine the strength of the hurricane season. And it's the conditions during August, September, October. So the essence of the seasonal hurricane outlook is really to predict the conditions within the main development region during August, September, October. This August, September, so far, we've had 6 storms formed in the main development region. All 5 became major hurricanes. So again, this is the core region. If you have a below normal season, you have very little activity in the main development region. An above normal season, you have a lot. Fortunately, it is this area where there's strong climate control over things like vertical wind shear, ocean temperatures, trade winds, etc. So fortunately, therefore, there is predictability for the season because there is predictability for this main development region. So the motivating concept behind the seasonal hurricane outlooks is that while hurricanes are obviously ultimately a weather phenomenon, the regional conditions within the main development region, which largely control the number, strength, and duration of the storms, those conditions often last for months or seasons at a time, and they have strong climate links. So therefore, by predicting these key climate patterns, such as ENSO and the AMO, and their combined impacts, you can often predict the regional conditions within the MDR that are actually controlling the hurricane season, and thus you can often say something intelligent about the overall strength of the season. We issue an outlook, a preseason outlook in late May to coincide with the onset of the hurricane season, and then we always issue an updated outlook in early August, and that is designed to coincide with the peak months of the hurricane season, which is by far when the bulk of the hurricanes and major hurricanes form. But there's more than just the numbers about the outlook, and when we issue the outlook, you know, the interviews and so on, press conferences and that, the other key message is hurricane preparedness. People need to prepare for every hurricane season regardless of the outlook. And we generally discuss in more detail, but just some key issues about preparedness, and things like your preparedness situations differ. They depend on your location, children, pets, finances, property, your transportation, the structure of your home. A lot of things go into consideration when you're preparing for the hurricane season. Of course, tropical storms and hurricanes can have many different impacts. So your hurricane preparedness plans really need to reflect both your personal situation and the types of storms conditions that you might expect or that are being predicted. This is the updated outlook that we issued on August 9th. We had indicated a high likelihood of an above normal season, possibly extremely active season, and as I mentioned, the season is extremely active. We had indicated a 60% chance of an above normal season and only about a 10% chance of a below normal season. So the model predictions, the conditions that we're developing as the summer went on were certainly indicative of an above normal, possibly extremely active season. And we had also indicated that this season could be the most active since 2010. Turns out so far it's the most active since 2005. But this is also the first extremely active season since 2010. So it's been a while since we've seen this level of activity. The outlooks are probabilistic. When we indicate ranges of likely ranges of named storms, hurricanes, and so on, we do so with basically a plus or minus 1 sigma range, roughly a 70% probability for each range, and that's what we verify the outlooks against. So for the August update, we had expected 14 to 19 named storms, 5 to 9 hurricanes, 2 to 5 major hurricanes. And so far, the activity that we've seen is certainly stacking up toward the higher ends of hurricanes and major hurricanes, but interestingly, named storms is still slightly a little bit below the forecast. Another parameter I'll talk about in just a second is ACE. It's accumulated cyclone energy, and that's a measure of the overall hurricane season strength. And the range we had predicted was 100 to 170% of median. What we've seen is the number so far is much higher, and that reflects this extreme duration and intensity of several of these major hurricanes. We didn't predict the extreme duration and intensity, as well as you know, compared to what's seen. So the time series here on the left is the ACE parameter. It measures the overall strength of the season by accounting for the combined intensity and duration of the tropical storms and hurricanes during the season. And the time series on the left here shows the seasonal ACE value for every year since 1950. And we use ACE to classify the season strength. When the blue bar, the ACE value extends up into the pink, the red area, that's above normal season. When it's above this green bar of 165, that would be called an extremely active, also people refer to it as a hyperactive season. When the ACE value is in the yellow range, that's what we classify as a near normal season, and then when it's down in the blue, it's a below normal season. Over at the right are the predicted ACE range, plus or minus 70% probability for May and then August, and you see that it's mainly in the above normal season with the possibility of being extremely active. And as the blue bar, thick blue bar at the right, shows that, again, the observed activity so far has exceeded the forecast. But what you see here is not just, is a lot, basically. We know there's a lot of multi-decadal variability to Atlantic hurricane activity. We had a high activity era during the 1950s and 60s, warm phase of the AMO, low activity era during the 70s, 80s, and 90s, and during that 24-year period, we only had 2 above normal seasons. Half the seasons were below normal with the cold phase of the AMO. We then switched back into the warm phase of the AMO in 1995, and since 95, we've been in a high activity era for Atlantic hurricanes. Many seasons have been above normal. Very few have been below normal. And in addition, many seasons have been, again, above the green line, have been hyperactive or extremely active. Clearly, this year is extremely active, and it's, as you can see from ACE, it is the most active since 2005. Now, when you're predicting these seasonal strengths, if you look at hurricane, our outlook is not a hurricane landfall prediction. It's just for the overall activity. But it turns out that when you get ACE above 165, when you get extremely active seasons, that's when the probability of hurricane and multiple hurricane landfalls in both the U.S. and the region around the Caribbean Sea go way up. And that's because you have so many storms forming in that main development region. They tend to be stronger, last longer, and track further westward, therefore putting the downstream areas, you know, the region around the Caribbean Sea and the U.S. at higher damage, and we've higher risk of landfalls, and we've certainly seen, you know, tremendous damage in both areas this year. On the right shows the contribution to ACE. The purple bar is our total ACE value to date. The red shows the contribution of ACE from storms that formed in the main development region. Clearly, then, you know, back to what I was saying before, it's the main development region activity that determines the season strength, and this year is no exception. The 5 major hurricanes that formed this year have produced 90% of the seasonal ACE. You don't get active seasons like this randomly. There tends to be a coherent and interrelated set of conditions that span the main development region, and everything comes together to produce a more active season. Things like the warm phase of the AMO. La Nina tends to favor stronger hurricane seasons. So I'm showing here a schematic of the conditions that we had based the prediction on, and these are pretty much the conditions we've seen so far. Warmer waters across the main development region. SSTs are on average 1 to 1.5 degrees C above average. Very weak vertical wind shear, which I'll show in a second, across the whole main development region. Stronger West African monsoon. And with that, you have weaker easterly trade winds, which means you have more deep tropical moisture getting into the main development region and more instability. At the same time, with the stronger West African monsoon, the African easterly jet is shifted further north, and there's more cyclonic shear due to the weaker easterlies along its southern flank. So as a result, easterly waves that are coming off of Africa can spin up much more easily from this combination of conditions. And we see this in most active seasons. And then as the waves move further westward, they're moving progressively over warmer water, weaker wind shear, and it's a perfect recipe for a lot of major hurricanes and significant activity. So the conditions we're seeing now and that we predicted are certainly consistent with the warm phase of the AMO. This is a map of the vertical wind shear Magnitude is in shading, and then the vector, shear vector is, you see the vectors. 200 to 850 vertical wind shear, it's typical wind shear that you look at. And this is the 60-day average, so basically over the last 2 months. I've indicated the main development region in the green box, and red values indicate where the shear is less than 8 meters per second. And on these time scales, that's generally 8 to 10 meters per second is really kind of the lower. When shear is below that, it's certainly conducive to a lot of activity. And what you see is the entire axis of very weak shear extending across the entire main development region, and importantly, encompassing the whole western portion, southwestern portion of the Atlantic Basin. We saw this pattern of very weak shear back in 2003, 4, and 5. So again, what this is indicating is that as these storms move westward, as the waves move westward and develop, they're not getting sheared off by the normal tropical upper tropospheric trough that's in the area. Instead, they're moving over very, very warm waters, extremely weak wind shear, a lot of moisture, a classic ingredient for storms in the western part of the basin. And we haven't, as I mentioned, seen this type of activity in the western part of the Atlantic in many, many years. In fact, people were, it's been 10 years since we had a major hurricane landfall. Well, we haven't had this pattern since 2003, 4, and 5. We haven't seen so many storms in the western part of the main development region. This is the key synoptic feature attributing to the excessive activity this year. And it's superimposed upon the warm phase of the AMO. This is another look at that feature. This is the top panel shows the 200 millibar stream function over the last 2 months. The blue circle is highlighting the area of this very amplified upper level ridge. Normally there would be a trough in that area extending down in the deep Caribbean, producing strong wind shear. That climatological feature is absent from the western part and is instead shifted farther east. Again, that's contributing to the very weak extended area of very weak shear, as I mentioned, similar to 2003, 4, and 5. But there's more to the picture than that synoptic feature. If you look at the stream function anomalies down at the bottom, I've indicated in the blue arrows, these are indicating where the subtropical ridges are amplified, and the red lines up on the top panel are showing the axes of those subtropical ridges. So we see amplified subtropical ridge across the entire Atlantic Basin, but also in the southern hemisphere. This interhemispheric symmetry of the anticyclonic anomalies is typical of the warm phase of the AMO. It's typical of a stronger West African monsoon, and it's typical of these very active seasons. One of the issues of one of the couple previous talks with dynamical model predictions, and one of the weaknesses with this season was predicting the extreme duration of the major hurricanes. These show the dynamical model predictions that we used in making the outlook. These were made in July for the August, September, October, November period, so for the remainder of the season, and then to the observed June, July activity is added in. And I'm just showing for major hurricanes here. We have the values for the various prediction parameters. Obviously, we didn't have any major hurricanes during June, July, so the forecasted numbers are for the ASLN are for the whole season. There's major hurricanes in the middle column, and then the predicted ACE range, plus or minus 1 standard deviation, with the middle of the range indicated in parentheses. Well, several of the dynamical models, when you look at the major hurricanes, they don't produce a major hurricane forecast. So predicting the number and duration of major hurricanes is very difficult still on a seasonal time scale. But it's that type of prediction that goes to the overall strength of the season. If you look at the dynamical model forecast for ACE on the right, generally the ACE values, if you're just looking at the medians, were 120, 116. Now here's one, GFDL 170. That had a very high, normally the GFDL produces extremely wide ranges in all the parameters. This year it happened to have a way up there in terms of ACE, but generally the other models were nowhere near that up there and not suggesting an extremely active season. The model averages I've shown in bold 90 to 160. So that's near normal, above normal season, but the middle of the ACE range is only 124. We've already seen about 228, so well above the predicted average. Our outlook was higher than the dynamical model average because we also used statistical tools, and it was also obvious that as the summer was progressing, things could really get very active. So in summary then, we pretty well predicted the overall conditions within the main development region that we've seen so far during August, September, and also correctly anticipated the potential for an extremely active season. We underpredicted the extreme duration of some of these major hurricanes. Predicted ACE was obviously too low. The extreme major hurricane durations, when you look at the maps, they're linked directly to that very strong and persistent ridge in the western part of the main development region in subtropical North Atlantic, and that is superimposed on the warm AMO. When you have that combination of conditions, you have a lot of activity like we're seeing this year. The strength of that, so in terms of the seasonal intensity and then these very westward positioning to these major hurricanes, that's linked to that persistent ridge in the western part of the basin. And the strength and persistence of that ridge is generally not predictable in the absence of La Nina. La Nina would favor more of a subtropical ridge in the western part of the basin. But in the absence of La Nina, it's essentially unpredictable, and we saw that basically in the dynamical models. So it remains very challenging to correctly predict the storm intensity and durations, especially these major hurricanes, and they're key components of the seasonal hurricane outlook. And so that's all I have, and I'll be glad to take any questions.
Great, Jerry, thanks so much for that very clear talk. And are there any questions in the room? I don't see any questions from folks online just yet. I actually had a question. I mean, you mentioned your increasing confidence from your first outlook at the end of May to your updated outlook in August. Can you talk a little bit about how your thinking kind of changed, or you became increasingly confident that there was going to be a very active season?
Sure. Well, back in May, a lot of the ENSO prediction models were indicating that El Nino could develop in time to affect the season. But what we saw instead was any warming in the Atlantic, or any warming in the central equatorial Pacific basically dissipated during July, just a very quick dissipation of that anomalous warmth. So El Nino never developed to offset what were more conducive conditions expected with the warm phase of the AMO. Another factor back in May was that SST predictions for the tropical Atlantic are quite challenging in the dynamical model still. There was a range of predictions about the anomalous warmth. Some models were predicting cooler than average SSTs in the main development region. Some were predicting warmer. As we went through the summer, the warmth in the Atlantic that we saw earlier in the year did not dissipate. Instead, it's maintained about 1 to 1.5 degrees C above average. So those were the main reasons for the increased prediction from the May outlook.
Great, thanks. So I don't see any more questions, and I think, unless there are any in the room, I think we can close here. I want to thank all the speakers for really interesting talks looking at this issue of predictability and prediction from kind of different angles, but looking at the extended weather out to even seasonal time frames. So thanks very much. And just as a reminder, this webinar, as well as yesterday's webinar, will be posted on our website within the next day or so, I think. And we encourage you to keep an eye out for forthcoming webinar announcements for the MAP webinar season. So thanks again for joining.